So hi everyone, I'm Susan Bates. I'm from the National Center for Atmospheric Research, and I'm going to be presenting results and the activities that we've been doing with a PRAC proposal at the Blue Waters facility. Our proposal is named High Resolution Earth System Modeling using Blue Waters capabilities. Right now our PI is Robert Rauber from the University of Illinois. Our original PI was Don Wubbles, and he recently took a position in the White House with the Office of Science and Technology. So Bob was gracious enough to step in and take that role for us. We do have collaborators at the University of Illinois, Maryland, and others at NCAR. I haven't listed all of them here so as not to use up the whole slide, but I wanted to point out Zach Zobel, who is actually here in the room, because he did provide some slides for this talk, and I'll also point out that he has a poster just outside, so if you're interested in his work, you can go see that a little bit later. So our proposal had three main objectives. The first was to better quantify future regional climate change by running high-resolution global coupled climate model, in this case namely the Community Earth System Model, or CESM, to meet the needs for the next generation assessments of climate change. And when I say assessments of climate change, I'm talking about the National Climate Assessment or the Intergovernmental Panel on Climate Change, IPCC, assessment reports. For the previous assessment reports, we used what we're now calling our medium resolution model. This is what we call the 1 degree model. It's roughly 1 degree in both latitude and longitude for all components of the climate model. And in this proposal, we wanted to push the resolution to better simulate storms and regional atmospheric circulation. Now, the sets of runs that we've done for this portion of the proposal are what I kind of call the highest resolution we can do for production runs. And what I mean by production runs are we do many hundreds or thousands of years of simulation doing different scenarios. So we may run 20th century historicals. We have various different future scenarios that we run. We might do one-offs where we're testing a particular process in the climate model. And for all of those, we generally want to do many ensemble members. And so it has to be a resolution of the model that we can do many different runs, but actually have an allocation that we can do them with. So the second objective was modeling studies on blue waters that will push the state of the art for such analyses. For this, we're doing the highest resolution we can possibly run. And so, of course, we have to be more selective about what types of scenarios that we run for those types of simulations. And these two first bullets are activities that are ongoing at NCAR. The third bullet is the work led by Zach at University of Illinois, and this specific studies to further clarify the understanding of effects of small-scale regional features. And for this, they're using the Weather Research and Forecasting, or WRF model, at 12-kilometer resolution over the U.S. Okay, so now I'm not going to go through all the details, but briefly introduce the simulations that sort of fell into those categories for the activities that are going on at NCAR. So we have this really great family of high-resolution simulations with the CESM. So the first set is the kind of resolution we can do for production runs. And so this is a 1/4 degree atmosphere land coupled to a 1 degree ocean sea ice. It's fully coupled, and what that means is that all of the components in the climate model, land, atmosphere, sea ice, land ice, there's a river transport model, and the ocean model are all active in these simulations. And we have various different standard sets of runs that we typically do with most of our production type simulations. Then we have the same resolution simulation. I'm going to have to do this left-handed. And in these cases, we wanted to be able to run many ensemble members, and so we're doing these as atmosphere only, which really means atmosphere and land are active. And these are so-called AMIP simulations. So we're forcing at the boundary with sea surface temperatures. And then we only did certain time periods, so we're calling them time slices. So for the present day, we're doing 1979 to 2012, and for future scenarios, we're doing 2070 to 2090. And then we have two different sets of future scenarios, one in which we created the ensemble by perturbing the atmosphere initial conditions, and one where we actually used different sea surface temperatures as the boundary conditions. And then this third set is where we're really pushing that model resolution. And for this, it's the same atmosphere, it's the same 1/4 degree atmosphere, but it's coupled to a tenth of a degree ocean sea ice model, and this too is fully coupled. And so it's really great to be able to have as many years as we do with this simulation, but we don't as you can see, like our future scenario isn't going to 2100, it's only going to 2050. And also I'll say that for this talk, we have a lot of great stuff that could come out of these runs, and we're sort of starting in on them. Been looking at some of them for about a year. I'm going to focus on precipitation just to kind of narrow it down and show you what kind of things we're able to do with these simulations. Okay, so why blue waters? So I threw up the cost of doing, if we were to do the entire set of each of those 3 bullets, how much it would cost on blue waters. And you can see that it's quite expensive. So we really do need big computers like blue waters to even enable us to get these sets of simulations with this resolution of the model. And just for reference, if we were using our 1-degree model, this medium resolution model, if we did everything you see on that screen, it would only cost us $2.5 million. So resolution really does play a role here in what we can do. I'll also point out that all of these runs at least had a portion of them run on blue waters. Some of them were run to entirety. Some of ensemble members may have been done on another computer, but everything you see here, at least a piece of it, was done with the blue waters computing system. Also, everything in white has been completed. And at the very bottom there, that future scenario, we've only gotten to about 2020 right now. So for those reasons, I'm actually going to be focusing mostly on the middle set of simulations, and then I'm also going to show some results from that first pre-industrial control simulation in the top bullet there. And I thought I was going to say something else about that, but maybe I'll just move on. Okay, so first I'm going to go through what do we get with high resolution? So why do we want to, for these types of studies, why would we want higher resolution models? Further along in the talk, I'm actually going to talk about changes that happen in the future. So we'll compare future to present day scenarios with these same simulations. So on the left there, you see what we call our nominal 1-degree model resolution. So this is the grid overlaying over the United States. And then on the right-hand side, this is our 1/4 degree grid. So you can see there are many more grid points over the United States. So we should be able to resolve much smaller scale features. And so what you hope with high resolution is that through better representation of topography and regional atmospheric circulation, that you're better able to represent these smaller scale processes. And so if I put up the typical size of a tropical cyclone, the inner circle is a typical diameter for hurricane force winds, and then the outer circle for tropical storm force winds. So you can see that with this 1-degree resolution, it would be awfully hard to represent a tropical cyclone, because at this inner circle you may have 1.5 grid points to represent it. So it's really not feasible to do that. And so we really need this 1/4 of a degree to be able to look at tropical cyclones. And so this is showing you how we are able to resolve these smaller scale features using topography, and that we do really improve topography as we go to higher and higher resolution. So this is obviously topography over the United States. The top left there is observations. The top right is our standard common 1-degree model. And then the bottom right is this 1/4 degree model. So you can really see that we're getting some smaller scale features standing out. Okay, so how do we do with mean precipitation? This is moving from the 1-degree model to the 1/4 degree model. So the top panel is showing the difference between mean precipitation, so it's a time mean from the model minus observations. And so those are model error biases in the model, and it's in millimeters per day. And so these deep reds are like 6 millimeters per day errors. And you can see that we have some fairly large errors in many places and over continents as well. In the bottom panel, you're looking at the difference between mean precipitation from the 1/4 degree model minus the 1-degree model. And so anywhere that the colors are opposite in these two panels are regions that the 1/4 of a degree model has improved the precipitation or mean precipitation over the 1-degree model. And so I'll just point out a couple of those places. Here in the Andes and inner Amazonian region, we really see a good improvement. Also the contiguous United States, there's improvement there. Indian monsoon region, and pretty much most of Africa, although I'm not sure you can see the coloring very well there. Okay, so what about extreme precipitation? Again, we're looking at the 1-degree atmosphere model compared to the 1/4 degree, and we're looking at probability of precipitation events happening. So on the x-axis, we have the millimeters per day. So on the right-hand side in that boxed region, these are really extreme events. These are very heavy precipitation events that don't happen very often. But these are typically the events that we're more interested in being able to model and predict. So if we blow that portion up, here is the line that is the 1 degree model representation of extreme precipitation. The black line is observations, and you can see that our 1/4 of a degree model really overlays those observations very nicely. This did not translate well to PC, but I think that you'll get the basic picture. So this is showing how we're able to resolve tropical cyclones with the 1/4 of a degree model. So the top left is observations, and what we're using here is we adopted a tropical cyclone tracking algorithm from the Geophysical Fluid Dynamics Laboratory. And you end up with the lines there are supposed to be showing you tropical cyclone paths, and the coloring is the intensity of the storm. So then if you compare the bottom two panels, where the left is the 1 degree and the right is the 1/4 of a degree, you can see we really aren't getting tropical cyclones at all in the 1 degree. So this is type of work that we're not even able to do with our 1 degree model, and so 1/4 of a degree is really opening up a new area for us. Okay, and this is an animation that I'm just going to start as I talk. So now we're moving into the difference between present day and future. So what you're looking at, these are the time slice simulations at a 1/4 of a degree that are forced by SST boundary conditions. The top panel is showing you 1 year of present day, and the bottom panel is 1 year out of the future, and this is just looping over daily averages of precipitable water. So the first thing that really stands out in this animation is that the bottom panel in the future, we're seeing a lot more moisture available in the atmosphere and than in the present day. And this doesn't mean that it's necessarily going to rain more, but it does mean that when it does rain, you could have a much heavier precipitation event in the future. These simulations are also nice because they're showing us features that we're now able to resolve. So you've probably been watching, and there might have been a hurricane scoop past in some of the basins. And then also these kind of filaments that stream out. You can see them pretty good in the present day. Those are atmospheric rivers, or so-called atmospheric rivers, that we're really starting to study at NCAR and elsewhere, and these are important for transporting moisture from the tropics into the mid-latitudes. Okay, so now looking at tropical cyclones compared between present day and future. These are cyclone density plots, and so the units here are average hours per year in which a storm is found within a 4x4 grid box. And so the deeper colors are showing you regions where we have more tropical cyclone activity. On the left is present day, and on the right is the future. Let's focus on the top two panels first. So this is all storms, so it's tropical cyclones all the way through Category 5 hurricanes. And what's interesting is that when you compare the future to present day, in these areas where you see most of the hurricane activity, it's actually decreasing in the future scenario. And you can really see that quite well in the Atlantic, that we're having a decrease pretty much everywhere of tropical cyclones. And then if we compare the bottom two panels, which is just plotting the densities for Category 4 and 5 storms, most of that activity is in the Western Pacific. And in the future, we expect to see more Category 4 and 5 storms. So this may mean that in the future there will be fewer storms, but when we do have one, it's going to be a stronger storm. This is just a different way to look at that relationship, and also the previous slide only showed one ensemble member from each of those present day and future scenarios, and now we're plotting all of the ensemble members that we have processed so far. So we actually have more, and we were trying very hard to get the analysis done before this meeting, but it didn't happen. But we can still see that same relationship. So now what we've done is we've found the number of storms each year of the simulation, and so there are 21 years here, and then that range is plotted in the vertical there. And so the leftmost plot is all storms, so all tropical cyclones. The middle is all hurricanes, and then the right is only major hurricanes, so the Category 4s and 5s. And again, we see the relationship that the black is observations. These blue are present day. The green is also present day, but it's it's flagged because it was perturbed in a different way. The red is our future scenarios, and again, the purple is also future, but it's one of the ones with different SST forcing. So in all tropical storms, we see that present day, there are more storms than in the future, so we'll have a decrease in those storms in the future. All hurricanes, it's a little bit harder to separate, but perhaps the same relationship, that we may have fewer total hurricanes in the future. And then major hurricanes, you can clearly see that present day compared to future, that the future, we're expecting more major hurricanes. Okay, so now this is moving into even higher resolution, and this is going on to the work being led by Zach at the University of Illinois. And so these are, this is work they're doing with dynamically downscaling over the contiguous United States, and they're using the WRF model at 12-kilometer resolution, and then they force the WRF model with initial conditions and boundary conditions from 3 different climate models, and so that's simulations 2 through 6. And then also with the inset reanalysis data. And then they've done various things. They can do spectral nudging or bias correction on those simulations. And those 2 methods are, will incorporate either observations or boundary conditions with the hope of improving atmospheric processes. And so, and then another thing that they did is after running all 6 of these simulations, they took the mean and the median, and they used that data also as a comparison, like a prediction, as well as the simulations. And the objectives for doing these types of things are to inform researchers why there are regional differences in the near surface climate extremes, and to better inform prediction methods. And so you'll be able to see in the next slide that they'll be able to tell, which model did better in which region, and did spectral nudging or bias correction help in this case. And then another objective is to provide stakeholders in the public with knowledge of the uncertainties on how climate change will affect the local hydrology processes and the heat stress on humans in a warmer climate. And so again, I'm sticking with precipitation here, but Zach's just submitted a paper, and they've looked at many more variables that are really important to us humans, such as heat index and temperature extremes and things like that. And so I do encourage you, if you want to see more of that, go see Zach at his poster a little later today. So here's one figure from the paper that describes extreme precipitation events. And so I'm not going to go into too much detail, but what they're plotting here is they've found the 95% threshold, which is what they use to define these extreme precipitation events, from both the model output as well as from observations, and then subtract the 2. So basically everywhere that you would see a negative number here are places where the model simulation is underestimating these extreme precipitation events, and if it's positive, it's overestimating those events. And so I'm gonna, and then these bottom 2 are their mean and median estimates minus the observations. And so I'm going to use this figure to show or talk about some of the conclusions from this paper. So the first is that the accuracy of extreme values are highly dependent upon region and boundary condition. And so as you look across these plots, you'll see that different models do better in different regions, and maybe even with different variables. And so there's a lot of range there. Second thing is, if we look at this mean and median prediction, you can see that they do a pretty poor job in predicting extreme precipitation. In both of these cases, they very much underestimate the extreme precipitation events. And this is because the act of taking the mean and median diminishes the variability. And then the third point is that many of the variables have the highest errors in the wettest and driest regions of the continental United States, and in regions where small-scale processes are common. And so the areas I've pointed to there in the southeast U.S. are places which all 5 of the climate model-driven simulations underestimate the extreme events in those regions. And it's likely because there are small-scale convective processes that happen in those regions that even at 12 kilometers, you're not able to resolve. So I'm just going to leave you with that kind of overall flavor of the type of work we're doing with the Blue Waters allocation. We have 3 papers that were either submitted or in press now or published that came out of this work. And I think, you know, we've got a really great group of scientists looking at these runs, and we have a really great set of simulations, thanks to Blue Waters, that we can really start to mine for all kinds of things now. So we greatly appreciate that.